Hey everyone, welcome back to the CyberNetters Networking 1 course. I'm Andrew Yick, and today we're going to dive into wireless networking, a crucial technology that keeps us connected without the need for physical cables, like what we talked about in the last video. In this session, we'll explore wireless media, the different IEEE standards that govern wireless communications, and how networks like Wi-Fi, Bluetooth, and WiMAX operate. Understanding these concepts is essential because wireless technology plays a major role in both home and enterprise networking, which provides flexibility, mobility, and scalability. We will also compare wireless and wired networks, and we'll be discussing key trade-offs such as cost, performance, and security. By the end of this video, you have a solid understanding of how wireless networks function and how to implement them effectively. Let's get started. So, let's talk about wireless media. Wireless media transmits data using electrical signals and the radio and microwave frequency ranges instead of using physical cables, like what we talked about in the last video. So, the wireless communication encodes data into waves or microwaves, which are then transmitted through the air to receiving devices such as laptops, routers, and mobile phones. The reason why you're able to watch these videos is because of these wireless communications, like sending the data through the air to your laptop or whatever device you're using. Wi-Fi, cellular, and satellite networks all rely on wireless transmissions. The signal are sent as electromagnetic waves, as mentioned earlier, which carries the binary data, which is the ones and zeros. And they're similar to how sound waves can carry speech. Interference can occur when multiple signals overlap or external sources disrupt the transmissions. So, some sources of interference can include outer Wi-Fi networks, especially on crowded 2.4 gigahertz bands. Microwave ovens, Bluetooth devices, and cordless phones can also interfere with the wireless communications, and physical obstacles like walls or metal objects can weaken them. So how do we mitigate it? We can mitigate it using the 5 gigahertz or 6 gigahertz Wi-Fi bands, which can reduce interference. There's also some security risk of wireless media because signals can travel through the air and it can be intercepted. So, some security threats of wireless media can include eavesdropping, like attackers can sniff wireless traffic if data is not encrypted. Also, unauthorized access, like if you set a weak Wi-Fi password, it can allow unauthorized users into the network. And there's also the man-in-the-middle attacks, also known as MITM, which attackers can intercept and modify transmitted data. So some security measures can include using WPA3 encryption to provide Wi-Fi networks and enable firewalls and VPNs to secure wireless communications. A few advantages of wireless media is mobility, how users can connect anywhere within range, and it is flexible because there's no need for physical cables. Just imagine how annoying it would be if you need to like carry a cable around and like plug it into like a wall or something just to get internet. As we mentioned earlier in the previous videos, standards are there to like make sure that like devices and like protocols and procedures from like different companies can come together and make sure they can like work together basically. So like standards for the wireless networks covers at both the data link and physical layers. So some common communication standards for wireless can be IEEE 802.11, which is basically the wireless LAN or the WLAN standard. The IEEE 802.15 is the wireless personal area network, also known as WPAN standard. And then the IEEE 802.16 is the wireless broadband access. There's also the global system of or for mobile communications, which is GSM, which is in charge of the data transfer over mobile cellular telephone networks. So let's start by diving deeper into the 802.11 standard. So, as we mentioned in the last slide, it is also known as the wireless LAN or the WLAN standard, which we call Wi-Fi, which is what we all commonly use. And then it uses carrier sense multiple access collision avoidance or CSMA/CA in order to control traffic and prevent collisions, which we'll be talking about later in this video. So, a wireless access point, also known as an AP, is a networking device that creates a Wi-Fi network by broadcasting a wireless signal, which can allow multiple devices to connect to a wired network wirelessly. So, the functions of a wireless AP is that it extends a wired network by providing a wireless connection, and it bridges the wired Ethernet and Wi-Fi for connectivity. A wireless adapter is a hardware device that allows a computer or another device to connect to a Wi-Fi network. It acts as a receiver which enables wireless communication with an AP. So the functions of a wireless adapter is that it converts the wired signals into wireless, and it supports different Wi-Fi standards, which we'll be going into later, such as the 802.11ac and the 802.11ax. Wireless adapters can be found in your laptop or a desktop or gaming consoles or smart TVs. I'm not gonna go too in depth in all these Wi-Fi standards, but feel free to pause the video if you want to take a closer look. But some key takeaways for these standards are that older standards such as the 802.11b and the 802.11g focus on range, like the newer ones like the AC and AX focus on speed. The dual band Wi-Fi, which is the 5 gigahertz and the 2.4 gigahertz, started with the 802.11n. And then the Wi-Fi 6, which is the 802.11ax, is the latest, which offers the best speed, efficiency, and security. Let's now talk about the 802.15 standard. So it is also known as the Wireless Personal Area Network or WPAN standard. It's commonly known as Bluetooth because it's the device pairing process to communicate only up to 100 meters, which is the short distance communication compared to Wi-Fi, which is the long distance. So the standard IEEE 802.16 is also known as the Wireless Broadband Access, which is commonly known as WiMAX, which is the Worldwide Interoperability for Microwave Access, which uses a point-to-multipoint topology to provide wireless broadband access. So you're probably wondering to yourself, why should I choose wireless? Well, one of the reasons, or two of the reasons why you should choose wireless is because of flexibility. Wireless networks allow easier mobility and scalability. It provides more flexibility for devices and users. Also, the main reason is cost. As you can see, less cabling and infrastructure is needed for wireless, which reduces labors and material costs. For example, in comparison, for switches and cabinets, wired needs more and wireless needs way less. For cabling, obviously, wired needs more and wireless needs less. For network adapters, similar quantities, but wireless adapters cost more per unit. For wireless access points, it's only required for wireless, and for PoE adapters, it's required in wireless for APs. So just as a reminder, a wireless local area network or a WLAN is a network that allows devices to connect and communicate without physical cables using the 802.11 standard or the Wi-Fi. So traditional business networks rely on wired LANs with Ethernet switches. Wireless LANs enable mobility, which allows the employees to access the network from anywhere in the office. And the growing demand for mobility has made VLANs essential for modern business operations. So, why are businesses moving to wireless LANs? Because it's flexible, it's scalable, and you save a lot, and it's good for collaboration and productivity. So, in the diagram shown at the top right, you can see there's four types of networks. You have the PAN, which is the personal area network, or the Bluetooth, like we mentioned before. The local area network, or the LAN, which is using the Wi-Fi standard, which is used for office and home networks. You have the MAN, which is the Metropolitan Area Network, which is for city-wide coverage, like the municipal Wi-Fi. And then you have the WAN, which is the Wide Area Networks, which is for like mobile networks, and it uses the GSM standard. I'm not gonna dive too deep in this slide, but feel free to pause the video if you want to take a look. But some of the key differences or the key takeaways between WLANs and LANs is that wired LANs offers the ability, speed, and security, but it requires physical connections. And wireless VLANs or wireless LANs offer mobility and ease of access, but it faces interference and security risks. Wi-Fi uses the collision avoidance, also known as CSMA CA, while Ethernet uses the collision detection, which is the CSMA/CD. So the data rates in wireless communications are influenced by the modulation technique used to encode data onto radio signals. The two key modulation methods in Wi-Fi are the DSSS and the OFDM. So the direct sequence spread spectrum, also known as DSSS, spreads data across a wide frequency range, which increases resistance to the interference. It uses one single channel transmission and spreads the signal across a broader bandwidth. Some pros is the lower cost and it's more resistance to interference, and the cons are it uses the lower data rates and it's less efficient. It's used in the 802.11b and G standards. You also have the OFDM, also known as orthogonal frequency division multiplexing, which is splits data across multiple subcarriers which transmits them in parallel. It allows higher data rates while reducing interference. Some pros are the higher data rates, which is more efficient than DSSS, and it's more improved resistance to interference. The cons are that it's more complex and it's a higher cost. It is used in the 802.11a, G, and N standards. So imagine a walkie-talkie that allows two people to communicate without a physical wire. Your wireless NIC is like the walkie-talkie that translates your word or the data into radio waves. The Wi-Fi router or the access point is like the outer walkie-talkie, receiving the signal and sending back a response. Just as walkie-talkie converts sound into radio waves, wireless NICs convert digital data into RF signals. A wireless NIC, also known as the network interface card, is a hardware component that allows a device to connect to a Wi-Fi network by transmitting and receiving RF signals. So, what does a wireless NIC do, you may ask? It enables wireless communication. It uses modulation to encode data, and it receives and decodes signals. So where are wireless NICs used? You can find it in your mobile devices like laptops, smartphones, and tablets, and desktop computers. Imagine you walk into a hotel lobby and you want to access your room. The receptionist, known as the access point, is your main point of contact. You don't go directly to the other guests or the devices, but instead you always communicate through the receptionist or the AP in this case to get what you need. Just like a receptionist connects guests to a hotel services, the AP connects wireless clients such as laptops and phones to the networks. Before you can use the hotel services such as the Wi-Fi or room access, you must check in at the reception desk. So in contrast, a wireless client must associate with the AP before it can access the network. This diagram shown represents a wireless network deployment within a large indoor space, such as a warehouse, a stadium, or a convention center. The four access points are strategically placed to provide Wi-Fi coverage across the entire area. So as you can see, there's four access points, which each AP broadcasts a wired Wi-Fi signal which covers a specific section of the building, which you can see the overlapping circles indicate the coverage area of each AP. So you may be wondering, why are there multiple APs? Having multiple APs can expand coverage because like a single AP wouldn't be enough for such a large area. And it also prevents dead zones and supports more users because it spreads network load across multiple AVs, which prevents congestion. Imagine you are in a busy room where multiple people want to speak, but everyone needs to avoid talking over each other. Since there's no central moderator, everyone must listen before speaking to prevent interruptions. This is basically how carriers sense multiple access with collision avoidance, also known as CSMA/CA, works in Wi-Fi networks. So carrier sense can be best described as listen before you speak. So in this scenario, before someone starts talking, they pause and listen to make sure that nobody is already speaking. In Wi-Fi networks, the devices do the same. Before transmitting, they sense the RF medium, which is the radio frequency energy levels, to see if it's already in use. That's where the wait for a pause comes in, which is the collision avoidance or backoff timer. Because if they detect RF energy above a certain threshold, they wait until the channel is free. And if two people start talking at the same time, neither will be understood. So to prevent this, when they detect someone talking, they wait a random amount of time before trying again. In this case, devices also use a random backup timer to avoid collisions when multiple devices want to send data at the same time. Let's talk about the CSMA/CA and the hidden node problem. So imagine two people, Alice and Bob, in a large park, both trying to talk to the same listener, which is the access point. So Alice is on one side of the park and Bob is on the other side. The listener AP is in the middle, and both Alice and Bob can talk to it. But the problem here is Alice and Bob are too far apart to hear each other. So the hidden node problem is here. Since Alice cannot hear Bob, she assumes that the air is clear and starts speaking. At the same time, Bob also thinks no one is talking and starts speaking. The AP hears both voices at once, which is a collision in this case, which makes it hard to understand each message. So this is how CSMA/CA tries to prevent this. So before sending data, a device listens to see if the channel is free. If it's clear, it sends a ready to send or an RTS signal to the AP. The AP replies to a clear to send or CTS if no one else is talking. The device then transmits its data, which reduces the chance of collision. So think of it like a walkie-talkie system. You say over before speaking if someone else is already talking. In the diagram shown here, which better pictures what I was talking about earlier, you can see how PC1 and PC2 can sense each other, and PC1, PC3, PC2, and PC3 can sense each other. But as you can see, PC1 and PC2 are far apart, so they cannot sense each other, but both the access point can sense both of them. Wireless routers can perform the role of an access point, a switch, and a router in a single device. They can allow multiple devices to connect to the internet via Wi-Fi or Ethernet. They act as a bridge between home and office network and the ISP. They also reduce infrastructure complexity by combining several network functions. So, when you set up a Wi Fi network, you can configure these wireless parameters, such as things focused on more compatibility, SSIDs, and channel selection. So, mixed mode, what it does is it lets you allow older devices to connect, which it lets both 802.11b and 802.11g devices to operate in the same network. And you can set the SSID, which multiple access points can share the same SSID to create a seamless network experience. So SSID is usually case sensitive, which is usually between 2 to 32 characters and is used to identify a Wi-Fi network. And then you can have the channel selection, which Wi-Fi channels can overlap, which leads to interference and reduced performance. So there are three different types of wireless network topologies. The first one is ad hoc mode. So in this mode, there's no access points or APs being used. Devices communicate directly within each other. It is the best for small temporary networks such as file sharing between laptops. Also, devices configure themselves, making it simple but limited in range and scalability. An example could be a group of laptops sharing files without an internet connection. For basic set service or BSS, it's also known as the infrastructure mode. So, an access point controls communications between clients, unlike the ad hoc mode where no access points are involved. The AP here acts as a central hub which allows devices to connect the wired network. The coverage of one area of one AP is called the basic service area or the BSA. So for example, a single Wi-Fi router providing connectivity in a small office or home or a cafe's public Wi-Fi network with one AP. Extended service sets, otherwise known as ESS, is multiple APs used for larger coverage. So it's basically the extended version of BSS. So multiple APs here are used to extend coverage, which creates an extended service area. Each AP has a unique MAC address, which is also known as a BSS ID, but shares the same SSID, which allows seamless roaming. So, for example, a large office or university campus with multiple APs that provides Wi-Fi across different floors. So the Common Distribution System, or DS, in an extended service set, ESS, allows multiple access points or APs to work together as if they're a part of a single basic service set, or BSS. This enables seamless roaming, which makes sure that device experience continuous connectivity without interruptions. Think of connecting to Wi-Fi like joining an exclusive club. So beacons are like the club advertisements. The club, which is the access point, sends out flyers, which are the beacons, and announcing its presence. And then you have the probes, which is looking for a club. You, which is the client device, walk around looking for clubs and ask who is open, which is a probe request in this case. Authentication is like the ID check, which is the bouncer, which is the AP, which checks your ID, password, or credentials. And then association is like entering the club. Once you're verified, you can enter and enjoy the club services, which is the network access. So beacons are like the Wi-Fi network advertisements as mentioned, which are sent by APs to broadcast their presence and available network settings. These devices listen for beacons to discover nearby Wi-Fi networks. And then you have the probes, which are searching for the networks, which are sent by client devices such as the laptop or phone to actively search for available networks. APs respond to probe requests if they match the requested SSID. And then you have the authentication, which is the identity verification. So, which is originally part of the early 802.11 security, which is still required in modern networks. It determines if the device is allowed to join, which is, for example, the password entry, the WPA2, the WPA3 authentication. Association is when you're connecting to a network. Once authenticated, the device forms a connection which is also an association with the AP. The AP then forwards data between the client and the network, which is the wired LAN or the internet. Thank you so much for watching. If you have made it this far, I truly appreciate your time and attention. If you found this video helpful, don't forget to give it a thumbs up and feel free to subscribe for more content like this. Do you have any questions or feedback? Drop them in the comments. I'd love to hear from you. Until next time, keep learning, stay secure, and I'll see you in the next video. Bye bye.